Welcome to the Deep Dive, your shortcut to understanding the complex systems shaping our future. Today, we are tackling a really big topic, diving into a stack of sources, everything from deep academic reviews on algorithmic bias to government reports on energy infrastructure,
Yeah.
and even some pretty dense legal analyses looking at autonomous contracts. We're aiming to move past the hype around artificial intelligence. We want to focus on three core questions. How is AI actually being governed right now? What happens when these autonomous systems, fail in the real world in critical sectors like energy or manufacturing? And ultimately, who picks up the tab, legally speaking, when a machine makes a decision without direct human input?
That's exactly right. And the sources we're looking at really force us to connect the dots, don't they? We have to link the sort of technical engineering side, building robust AI, with these huge legal and ethical questions about accountability. We'll be covering the basics needed for fairness and transparency, but also the really transformative applications and, frankly, the risks in areas like the power grid and industry.
Yeah, our goal here is to give you that comprehensive shortcut. We want you to walk away with a solid grasp of three main systemic areas. First, those essential frameworks for ensuring fairness, security, and accountability in AI. That's non-negotiable. Second, how AI is changing things and the risks involved in the modern energy grid and the industrial IoT. And finally, we'll get into that really cutting-edge intersection of AI, blockchain, and legal liability, especially where human control starts to fade. Okay, let's unpack this then. We really have to start at the foundation, right? Building trust in these systems that learn on their own.
Absolutely. Building trust, what we're calling the trust equation here, it really hinges on tackling bias. And the documents are crystal clear on this. Biased AI isn't just about getting the wrong answer sometimes. It leads to discriminatory predictions. And that has real-world impacts on civil liberties, on safety, on the quality of services people get, especially for certain groups. Think about a biased AI in loan applications. People get unfairly denied money. Biased emergency service dispatch, unequal response times. The stakes are incredibly high.
And one thing that really jumped out from the reviews we read is how we use the term bias. It's not just one thing, is it? We need to be specific.
Precisely. There's a lot of confusion, actually. People mix up the narrow technical idea of statistical bias with the much bigger problem of biased AI systems. Statistical bias is, well, technical. It's about uneven error rates. Maybe an algorithm is 98% accurate overall, but only 90% accurate for a specific demographic because they weren't well represented in the training data. That needs technical fixes, things like adjusting sampling weights or optimizing fairness metrics.
But then you have the deeper problem, where the AI is just reflecting the biases already out there in society.
Right. That's biased AI systems.
Yeah.
These systems learn from real-world data, and that data, it's a snapshot of existing inequalities, historical exclusion, the human preferences.
Right.
It's not neutral. So the AI ends up perpetuating or even amplifying the discrimination it learned. The data itself isn't objective.
Which means just trying to clean the data isn't always enough. The bias can be baked in right from the start, from how the data is even generated or labeled. Can you give an example of that?
Sure. Let's stick with classification. It's used everywhere in AI. Think about gender classification. Often, to build a model, developers need simple binary inputs. Male, female. It's a technical constraint. But that forces complex, fluid identities into these rigid boxes. So when you deploy tools using this like image recognition, they structurally erase or misclassify anyone who doesn't fit neatly. That choice, made during data labeling, inherently limits fairness.
So, okay, if you're an organization trying to mitigate this, you need to look for several specific types of data bias, not just one general bias. What are the main ones?
Yeah, the sources really emphasize looking at multiple layers. There's sample bias. Your training data doesn't cover the whole picture. Like the classic autonomous vehicle trained only in sunny daytime conditions. It's going to struggle at night or in fog, right? Then you've got historical bias, reflecting past societal wrongs. Sampling bias, which is about how you collect the data. Label bias, where the humans labeling the data introduce their own prejudices. And measurement bias, where the tools you use to collect data aren't accurate for everyone. Tackling this really needs, well, a village. Diverse teams, input from social scientists, domain experts who get the context.
Okay, so identifying the problematic data is step one. Then you move to the algorithm itself. What did the systematic review say about the best technical ways to actually build fairness into the algorithm during training?
Right, so when you get to the training phase, the goal changes a bit. You're not just optimizing for raw accuracy or precision anymore. You start explicitly optimizing for fairness metrics too. The two most common methods popping up everywhere in our sources are regularization and adversarial training.
Regularization sounds Technical. How does that actually enforce fairness in practice?
Think of it like adding a penalty. Normally, an algorithm just wants to minimize its prediction errors. That's its main goal. With fairness regularization, you add another term to that goal. This term penalizes the model if its predictions create unfair disparities between different protected groups. So the algorithm is forced to find a balance, minimize errors, and minimize discrimination. It might give up a tiny bit of overall accuracy, but it gains significantly in fairness.
Interesting. And adversarial training, that sounds like you're setting algorithms against each other.
That's basically it. It's quite clever, actually. You have two neural networks. One is the predictor. It tries to make the main decision, like approve a loan. The second is the adversary. Its job is to try and guess which protected group the predictor used information about to make its decision. If the adversary can easily guess, the predictor gets penalized. This forces the predictor to learn not to rely on those sensitive attributes, pushing it towards making decisions that are independent of things like race or gender.
That's a really interesting dynamic, sort of self-policing. The sources also mention some emerging approaches. Could you maybe explain one like deep fair or fairly clustering, just briefly?
Sure. Let's take fairly clustering. You know how standard clustering algorithms group similar data points together? Well, fairly clustering adds a fairness rule. When it creates these groups, or fairlates, it insists that each little cluster must reflect the overall population's demographic breakdown. So if your whole data set is, say, 60% group A and 40% group B, each fairly creates has to be pretty close to that 60-40 split too. This stops downstream algorithms from starting with skewed representations.
But even with the best technical fixes, it doesn't matter if the organization itself isn't set up for fairness. Which brings us to governance. For a company, this isn't just about being ethical, right? It's serious risk management.
Oh, absolutely. It's like the ultimate insurance policy. Properly addressing bias and setting up clear accountability. That mitigates huge financial risks, protects the brand's reputation, it enhances the value proposition, and critically, it gets the company ahead of the curve on regulations that are definitely coming, flying blind without governance. That's just asking for a PR disaster or a massive fine down the line.
So what are the first steps an organization needs to take to build this oversight?
First things first, risk assessment. You have to map out all your AI use cases, current and planned, then rank them by potential impact. Which ones could affect people's rights, their health, their finances the most? Those high-risk applications need the tightest controls and the most resources.
And the people involved, the governance board, it needs more than just different job titles, right?
No.
It needs diverse perspectives.
Essential. Absolutely essential. The AI governance board needs genuine diversity, gender, race, functional expertise like legal, compliance, IT, but also different levels of seniority, different lived experiences. Why? To catch the blind spots. A lawyer sees legal risk, a social scientist sees community impact, an IT lead sees technical hurdles. You need all those views to surface the hidden systemic biases that one group might totally miss.
Okay, so you've got the board, you've assessed the risks. How do you make sure the controls actually work once the AI is out there? That's where auditing comes in.
Exactly. And internal audit can't just be a checkbox exercise here. They need to be deeply involved in the AI strategy. Auditors have to really dig into deployed algorithms. What does it do? What data does it use? What are the risks? What are the ethical issues? And they need to assess the controls management has put in place. Our sources specifically point to frameworks like the IIA's AI auditing framework that emphasizes coordination between governance, management, and audit, and aligning with the big one, the NIST Artificial Intelligence Risk Management Framework, AI RMF 1.0. That's becoming the standard.
All this accountability, though, kind of relies on us being able to understand why the machine made a particular decision, which hits the infamous black box problem in complex machine learning.
Ah, yes, the black box. It's the paradox of deep learning, isn't it? We create these incredibly powerful systems. They make super accurate predictions. But the way they reach those predictions involves so many parameters, so many nonlinear calculations, that often even the creators can't pinpoint the exact reason for a single output.
Yeah.
That lack of transparency is a major barrier to trust and accountability.
So the answer is explainable AI or XAI, but it's not just one magic bullet, right? The sources talked about different levels: transparency, interpretability, explainability. Can you break those down?
Sure, let's use a loan application example. Transparency is the most basic level. It's about knowing how the model works, having access to the code, the data it trained on, its architecture. You know the ingredients, the recipe, but you don't necessarily know why the final decision was made for your loan. Interpretability goes a step further. It's about understanding the relationships the model learned. You might be able to see, generally, that factors like high debt lower the score. But still, maybe not why your specific application was denied. Explainability is the most practical goal, usually. It focuses on explaining a specific decision. For that rejected loan applicant, an explainability tool should provide a clear, human-readable reason. Your application was denied mainly because your credit utilization is over 40% and your employment history is less than 2 years. That's actionable.
Right, that clarity is vital. So organizations need tools that translate the AI's logic into something everyone can understand, the customer, the employee, the regulator.
Exactly. And the sources really stress this. You need to be transparent, not just about what the model can do well, but also about its limitations, its known weaknesses, its potential pitfalls. That's just fundamental to deploying AI ethically.
Okay, we've laid out the groundwork for governance and trust. Now let's pivot. Let's move from these principles to where the rubber meets the road, high-stakes applications in the physical world. Energy, materials, industrial machines, where AI decisions have immediate physical consequences. Right, let's talk about the energy grid. The U.S. grid is going through this massive transformation. We're moving away from the old model, big power plants sending power one way, to this incredibly complex system managing power flowing in all directions, from solar panels, wind farms, batteries. It's dynamic, it's variable. And managing that complexity, that speed, it seems like AI is becoming essential.
It's a total paradigm shift, absolutely. The old grid was relatively predictable. The new grid, it's operating right at the edge, constantly balancing supply and demand from thousands, millions of sources. AI is critical for that near real-time balancing act, for integrating all these variable renewables and just managing the sheer complexity of it all.
So, based on those government reports we looked at, what are the top priorities for using AI to make this clean power grid a reality?
They really fall into three main buckets, driven by need and policy. First up is operations and reliability. AI is dramatically better at forecasting renewable energy output, predicting solar and wind availability hour by hour using weather data, historical patterns. It also optimizes the power system itself, making the computations needed to manage these flows much faster. And critically, it helps operators spot anomalies before they cascade into major outages.
And the second area, making sure the grid can handle shocks, like extreme weather.
Exactly, that's resilience. We're seeing more extreme weather, heat waves, freezes, big storms. AI tools offer much better accuracy and specificity in predicting where outages are likely to happen. That lets utilities take proactive steps, pre-positioning repair crews, maybe strategically isolating vulnerable parts of the grid.
And the third one is about actually building the new stuff faster.
Precisely. Permitting and siting. Getting new transmission lines or renewable energy projects approved and built takes ages. It's a known bottleneck. So AI models, including potentially these large foundation models, are being tested to speed up the whole process, finding the best locations faster, processing environmental reviews, navigating the complex permitting paperwork much more efficiently than humans alone can.
Let's dig into that conceptual diagram we saw. It showed this AI orchestrator at the heart of managing the grid. Can you walk us through how that might work during, say, a major heat wave?
Okay, imagine a sudden, dangerous heat wave hits California. Demand spikes, threatening blackouts. At the center, you have the Power Grid Foundation model. Think of it as a massive digital replica of the grid, its physics, its components, its history. The AI orchestrator sees the heat wave coming, detects the looming demand spike, and kicks off a coordinated response. It calls on different specialized AI agents. The forecast agent pulls in real-time weather data, historical load info, renewable predictions, and tells the system exactly where demand will peak and where solar power might drop off. At the same time, the algorithm agent runs incredibly fast optimization calculations, finding the best way to reroute power from areas with surplus, potentially adjusting flows in milliseconds. This used to take hours.
And the human operator needs to know what's going on instantly, right?
Absolutely. That's where the intelligent dashboard comes in,
Yeah.
powered by the Q&A agent. It gives the operator immediate, clear answers. Like, okay, these specific peaking power plants in LA, San Francisco, and San Diego need to come online now. It also confirms coordination with external systems, maybe telecom networks, to prevent cascading failures. The orchestrators, like the conductor, making sure all these fast, automated decisions work together for stability.
That level of automated coordination sounds powerful, but it all depends on good data. What are the big challenges around data and security for a system like this?
Well, on the data side, there's a persistent gap. The energy industry has tons of detailed, sensitive data, actual power flows, sensor readings, but researchers who could build better AI models often can't get access to it due to confidentiality. And climate change makes it harder too, because historical data isn't always a reliable predictor of the future anymore. The patterns are changing.
So how do they work around that data access problem?
One really promising approach mentioned is synthetic data. Basically, using AI to generate artificial but realistic data sets. These synthetic data sets mimic the statistical properties of real grid data, but without revealing sensitive details. They can then be fine-tuned and validated using AI to make sure they're accurate enough for researchers to use safely. It could really speed up model development.
Okay, now security. If an AI is calling the shots, maybe attackers don't need to hack the control system directly. They just need to fool the AI.
That's the scary part. AI opens up new attack vectors. The big one is adversarial attacks. These are subtle, carefully crafted manipulations of the input data. The goal is to trick the AI into making a bad decision. An attacker might slightly tweak sensor readings from a transformer just enough to fool the AI orchestrator into misjudging its stress level, maybe leading to a dangerous power rerouting hours later, but not enough to trigger a simple alarm.
So they're exploiting the AI's mathematical blind spots, essentially.
Precisely. And the other huge risk is software supply chain risk. These complex AI systems rely heavily on shared components, open source libraries, common foundation models. If an attacker compromises one popular library or poisons the training data of a widely used model, they could potentially infect hundreds of critical systems at once. Securing that supply chain is absolutely vital.
Shifting gears slightly, AI isn't just managing the grid, it's also speeding up the discovery of the new materials needed for clean energy, right?
Yes, is acting as a powerful scientific accelerator. AI is really changing the game in material science. It allows researchers to discover new high-performance materials much faster. Things like better battery chemistries, more efficient catalysts for producing hydrogen, new materials for capturing carbon dioxide. AI can screen millions or billions of potential candidates computationally.
How does that look in a modern lab? What's this idea of a self-driving lab?
A self-driving lab is amazing. It combines AI with robotic automation. The AI designs an optimized plan for experiments, say, finding the best new catalyst. It figures out what parameters to test. Then, robotic systems actually do the experiments automatically, mixing chemicals, heating things, measuring results thousands of times, incredibly fast. All that data feeds straight back to the AI, which learns from the results and designs the next round of experiments even better. It creates this closed loop of discovery that's orders of magnitude faster than traditional methods.
And large language models, the LLMs everyone talks about, do they fit in here?
They do. LLMs are great at processing huge amounts of text. They can read and synthesize vast scientific literature and millions of research papers. They can spot trends in materials properties, summarize entire fields of research, even infer potential properties of new materials before they're made in a lab. It's like having a super intelligent research assistant.
And finally, managing the actual physical infrastructure for things like carbon capture or hydrogen.
That's where digital twins become really important. A digital twin is a constantly updated virtual replica of a physical asset, like a pipeline or a storage tank or a turbine. It uses real-time sensor data from the physical system combined with physics models. For carbon transport or hydrogen systems, these twins help optimize operations, maybe predict combustion efficiency in a hydrogen turbine, or identify potential stability issues before they happen. They can even suggest or trigger corrective actions. Often, hybrid models combining AML with traditional physics are used, especially for safety-critical functions.
Okay, let's zoom out again. From the grid to the factories and warehouses that power the economy, predictive maintenance driven by AI seems like a revolution for the industrial Internet of Things, or IIoT.
Predictive maintenance, PDM, yeah, it's probably one of the most immediate and tangible benefits of AI in the physical world right now. Instead of fixing things after they break, or on a fixed schedule, PDM uses sensors monitoring vibration, temperature, sound, power usage to predict exactly when a component is likely to fail. For expensive industrial machinery, that's huge.
And the efficiency gains reported in the sources are staggering. Just how big are we talking?
The numbers are really impressive. Companies using these smart PDM systems are reporting maintenance cost cuts of up to 30%. Even more importantly, unplanned downtime, which kills productivity, can be reduced by as much as 75%. Overall, machine downtime often drops by 50%, which can extend the life of the equipment by 25–30%. And it's not just about money, there are safety benefits too. Reports show around a 24.7% drop in safety incidents linked to equipment failure, plus energy savings around 13.5% and waste reduction near 16.8%.
Wow, those are game-changing numbers. What kind of technology setup do you need to make this real-time prediction work?
It generally relies on a hybrid edge cloud architecture. You need speed, but you also need long-term learning. So edge computing handles the speed. You have AI models running right there on the factory floor, close to the machines. They process sensor data locally, detect anomalies in milliseconds, and trigger immediate alerts warning an operator about dangerous vibrations right now. Then, the cloud platforms do the deeper analysis. They gather historical data from maybe hundreds of similar machines across the company over years. Sophisticated cloud-based AI models use this big-picture view to refine the predictive algorithms, making future predictions even more accurate and optimizing maintenance strategies. This combination fast edge alerts plus deep cloud learning is why issues are often spotted, on average, 15 days earlier than with traditional methods.
Whether it's the grid rerouting power or a factory scheduling maintenance, the common thread is less direct human intervention. This drive for efficiency seems to inevitably push us towards fully autonomous systems. And that's where the legal system starts to really grapple with things. Right? This relentless drive for efficiency seems like it's heading towards fully autonomous supply chains. Procurement, for instance, is often mentioned as a prime candidate. AI agents finding suppliers, negotiating prices, placing orders, all without a human okaying it. But when you take the human out of the loop, how do you assign responsibility both morally and legally when things go wrong?
This forces us right into the concept of meaningful human control, MHC. It's a framework that actually came out of debates around autonomous weapons, but it's incredibly relevant for civilian AI too. The core idea of MHC is that for decisions with significant consequences, humans must remain morally responsible, not the algorithms.
And for MHC to hold, there are two key conditions that need to be met, according to the sources.
That's right. They are the tracking condition and the tracing condition. The tracking condition basically means the AI system has to be responsive to human moral reasons. It needs to operate within the ethical boundaries and objectives humans set for it. The tracing condition is about accountability. The system's design must allow any outcome, especially a harmful one, to be traced back to at least one specific human decision somewhere along the line: design, development, deployment, operation.
And it's that tracing condition that advanced self-learning AI really threatens to break, isn't it? Especially when systems adapt and change over time on their own.
Exactly. When an AI becomes a black box constantly optimizing itself in ways humans can't fully predict or understand, that traceability gets lost. The AI might still achieve the overall goal you gave it, like maximize efficiency, but the specific steps it took might be inscrutable. If those steps lead to harm, you can no longer clearly point to a specific human error in design or operation. And that's where traditional legal frameworks like negligence really struggle.
Yeah, negligence law seems particularly challenged. It usually requires proving a human failed to act reasonably and could have foreseen the harm.
Trying to apply that to an opaque, evolving AI is incredibly difficult. Foreseeability is the key problem. How can a manufacturer reasonably foresee every possible negative outcome from an AI designed to continuously learn and change? When an accident happens, proving breach of duty that someone was careless becomes almost impossible if you can't understand the AI's internal state. And proving causation, a nightmare. Was it the programmer's fault, the users, the
Yeah.
data providers, or some emergent behavior within the AI itself? It gets very murky very fast.
This legal fog gets even thicker when we talk about contracts, especially smart contracts. These blockchain-based programs are designed for rigid, automatic execution.
Right. They promise automation, like automatically releasing rent payment when a paycheck hits or releasing escrow funds when a project milestone is verified. But they have a fundamental limitation: off-chain reliance. Smart contracts live on the blockchain. They can only act on data on the blockchain. Many useful applications need real-world data weather information for crop insurance, shipping data for logistics contracts. This data comes from outside the blockchain via sources called oracles.
And bringing in that outside data creates a potential point of failure because blockchains demand perfect agreement, right?
Exactly. Consensus failure is the Achilles heel. The data has to be pushed to the contract by the oracle, and every node in the network running that contract needs to see the exact same data at the exact same time. But real-world data fluctuates. Imagine that crop insurance contract needing temperature data. If one node gets a reading of 31.9 degrees and another gets 32.0 degrees just a fraction of a second later due to tiny sensor variations or network lag, the network can't agree. Consensus fails. The condition, temperature below 32, is marked not satisfied, and the insurance payout doesn't happen, even if the temperature did drop. Funds get locked.
That really highlights the clash between the tech ideal code is law and legal reality. The DAO hack fantasy showed this years ago.
The DAO was a major lesson. It pitted the purist view that the code should run exactly as written, bugs and all, against the practical need to intervene when flawed code leads to unintended, disastrous consequences. The source material makes it clear. Even for simpler smart contracts, parties often want some kind of third-party verification that the code actually does what the plain language agreement says it does, because reading the code itself, often impossible for non-programmers.
So there's a lot of work going into bridging that gap between human intent and the rigid code.
There is. One key area is developing tools that can automatically generate accurate, human-readable formal specifications from plain English descriptions of what the contract should do. Think of standards like the ERC20 token standard. Being able to formally verify that the code meets the specification helps developers test that the contract will actually achieve the intended outcomes, reducing ambiguity and potential disputes.
Okay, taking automation even further, we get to self-driving contracts, SDCs. This sounds like contracts that can literally change their own terms after they're signed.
It's a big conceptual jump, yeah. SDCs aren't just executing preset terms. They contain logic that allows them to adapt and effectively rewrite parts of their terms based on changing conditions defined in the contract. This often works through something called a contractual micro-directive. It's like a mini-law within the contract. You agree on a general goal upfront, say, maintain high product quality. The algorithm then translates that goal into a specific executable action later, like automatically increase quality checks by 15% if sensor X detects a deviation.
So it kind of solves that old legal tension between having flexible standards versus rigid rules.
That's the idea. It tries to give you the best of both worlds. You get the certainty of a rule because the micro-directive is executed precisely by the machine, but you also get the adaptability of a standard because the specific directive is generated dynamically based on the current situation. This could be really useful for complex, long-term agreements where you can't foresee everything. We might see a market emerge for certified SDC code providers, maybe insurers, arbitration services, or even big platforms like Uber or Airbnb offering these.
All these autonomous systems, machines making decisions, contracts executing themselves, bring us right back to that core problem, liability. Who pays when harm occurs? Current laws are clearly struggling.
And nowhere is that struggle clearer than in Europe, where they've been trying, and largely failing, to create consistent liability rules across all the member states. The main tool was the Product Liability Directive, PLD. But it's based on proving a product was defective, that the defect caused damage, and linking it back to the producer. For opaque AI, proving that causal link and the defect is incredibly hard for victims. So not many cases were brought into the PLD, people fell back on varying national tort laws, and the whole system stayed fragmented.
So the EU tried to patch this with the proposed AI Liability Directive, ALAD. What was its approach and why did it face so much criticism?
The ALD tried to ease the victim's burden of proof, especially for high-risk AI systems. It introduced things like procedural presumptions. If certain conditions were met, causation might be presumed, and obligations for developers to disclose information. Basically, it aimed to make it a bit easier to sue successfully. But the critics, many legal scholars among them, said it was tinkering around the edges. It offered only modest procedural help without changing the underlying substantive liability rules. Member states would still have their own different fault-based systems, so it wouldn't actually create harmonization or reduce the complexity and uncertainty of cross-border litigation.
Which is why the European Commission is now reportedly thinking about just withdrawing the ALD proposal altogether and focusing elsewhere.
That seems to be the current thinking, yes. The focus seems to be shifting towards ex-ante regulation rules aimed at making AI systems safe before they're deployed, like the Big AI Act, rather than harmonizing the ex-post liability rules for when things go wrong after deployment. And many in the legal field are worried this leaves a significant gap when it comes to compensating victims who are actually harmed.
So what's the alternative that legal experts propose? What would actually provide the needed clarity for AI liability, especially for high-risk systems?
The strong argument from many experts is for a specific strict liability regime, but narrowly focused only on designated high-risk AI systems. Strict liability means liability without fault. The injured person wouldn't need to prove the AI developer or operator was negligent. They just need to prove the high-risk AI system caused their harm. The liability would typically fall on a single entity, usually the operator who controls the AI and benefits from it economically. This provides clarity, predictability, makes insurance easier to price, and shifts the focus from complex fault-finding litigation to efficient risk management and compensation.
Which brings us to the most provocative idea in the source material. If these systems become truly autonomous, Should they have some kind of legal status themselves? The idea of AI legal personhood.
Yeah, it sounds radical, but it's not entirely new. Back in 2017, the European Parliament actually floated the idea of creating a specific legal status for very advanced AI. They call them electronic persons.
Hmm.
The thinking is, if an AI is making genuinely independent decisions that have consequences, maybe it needs its own set of rights and, crucially, obligations.
What would that actually mean in practice?
Well, the implications could be huge. An electronic person might be able to be named as a party in a lawsuit. It might be legally required to have insurance to cover damages it causes, funded perhaps by its owner or creator. Proponents argue this could actually enhance accountability by creating a clear point of responsibility, and maybe even foster innovation by reducing legal ambiguity for developers. Now, let's be clear. True artificial general intelligence, AGI, is still theoretical. Most AI today is narrow AI, designed for specific tasks. But the conversation is happening globally. You had Saudi Arabia granting citizenship to the robot Sophia a few years back, largely symbolic, maybe, but it shows that governments are thinking about the status of non-human entities making decisions with real-world impact. Hashtag tag outro.
Okay, so this deep dive has really underscored one major theme. AI technology is advancing incredibly fast, and our governance and legal systems are playing catch up with this increasing autonomy. We saw the absolute necessity of strong internal AI governance, things like diverse teams, using solid risk frameworks like NIST, and demanding explainable AI so we know what's going on inside the black box.
And we also saw the clear, immediate payoffs in the physical world. Predictive maintenance cutting industrial downtime by potentially 75%. The AI orchestrator managing the immense complexity of the future energy grid. Even AI accelerating the discovery of vital new materials for clean tech.
But then, crucially, we traced how that push for autonomy, minimizing human involvement for efficiency's sake, puts immense strain on our legal structures. We looked at the confusion around negligence for autonomous systems, the practical headaches of smart contracts relying on real-world data, and that really critical debate in Europe about whether strict liability is needed, especially since the focus seems to be shifting away from harmonizing compensation rules.
Yeah, connecting it all, the big picture seems to be that our drive for AI autonomy, whether it's in supply chains or energy, is moving faster than our ability to build the legal and ethical guardrails. Governance needs to be about more than just efficiency. It has to embed values like meaningful human control. And if the main regulatory focus becomes just preventing harm up front, rather than ensuring compensation after harm occurs, that leaves a real potential justice gap for people affected.
Which leaves us with a really important question for you, the listener, to think about. We're pursuing these incredibly precise autonomous systems like self-driving contracts, partly because they remove human error and ambiguity, control is delegated to the algorithm. But when efficiency seems to demand we minimize direct human agency, how do we ensure these systems still operate according to our moral reasons? And perhaps more urgently, how do we guarantee that when harm inevitably does occur, there's a clear, fair, and efficient way for victims to get redress? When the code becomes the final authority, where does human justice fit in?